p-value. Now, when we read p-value from the text, it's very confusing. Okay, I'm going to write it down so that we can read it a multiple times and then we'll relate it to whatever we have to do. The p-value is the probability calculated assuming that the null hypothesis is true. Okay, this is what we've been doing throughout. We're assuming that the null is true. And what are we calculating? We're calculating the probability of obtaining a value of the test statistic at least as contradictory to H naught as the value calculated available sample. Okay, looks like complicated hocus pocus. Okay, so let's just get back to what we've been doing. The same example, same null hypothesis. Null hypothesis was theta, the population parameter defined as differences in proportion of people showing improvement. This was going to be 0, and the alternate one was that they're not same. Difference is not 0. So this is still the distribution of test statistic. This was centered on 0. We have 1, we have 2, -1, -2. Okay. The calculated value of the test statistic was, we don't need this 2. Okay. 1. This was 1.99. Okay. I'm going to use blue color now. Red I used for rejection region, critical value. And we also need now they should be same actually. The tails should be similar. Okay, so we're still doing a two-tailed analysis because our alternative hypothesis is such that. Now let's read this out. The p-value is the probability calculated assuming the null hypothesis is true. So this distribution is drawn assuming the null hypothesis is true. We're going to calculate the probability value of obtaining a value of the test statistics at least as contradictory to H naught as the value calculated from available sample. This is the value calculated from available sample. Now we need the probability of more values which are at least as contradictory. That means they are either contradictory to the same level or more contradictory. More contradictory would mean more away from this center. Okay, what is this probability? This probability can be obtained from standard normal tables, and tell you the probability value here, p value for t is equal to 1.99 is 0.047. Okay, so how do we calculate probability value for t? We know the distribution, and it's a standard distribution. There would be a standardized table for that. All we need to know is what is the probability of what is the area to the right of this, and because it's standard normal combined, what is this area of having values less than minus 1.99 and more than 1.99. Okay, it's very easy, you should have known this. I'll just show you after this how to get this area for standard normal. Okay, you can get it for any value. It's very easy to know what is the value of area under the curve to the right of 1. Just have to look at the standard normal table. Alright, so does this hocus pocus now make sense? Here, let me read it out again. 1/2 is calculated assuming that the null hypothesis is true. We concluded that part by saying that this distribution is drawn assuming null hypothesis is true, of obtaining the value of test statistic at least as contradictory. Okay, if it's far away from the center, it is contradictory to null hypothesis, at least as contradictory as the one calculated from the available sample. The probability value then is area in the extreme tails, which is the probability of getting more extreme values, or at least this one. This is what it is. Okay, now few basic rules. If your and say level of significance is denoted using alpha. Okay, the level of significance chosen in our previous example was 5%, so alpha was 0.05. Now if p value is less than alpha, what do? We reject null hypothesis, and we shouldn't be saying we reject. You should say we have gathered enough evidence to infer that the null hypothesis is not true. This is the technically correct language of saying. Okay. Infer that null hypothesis is not true. And if p value is greater than alpha, okay, then we say we fail to reject null hypothesis. We fail to say that this is not true. Okay, you never say that you accept this, you just say you fail to reject it. You don't have enough evidence to be able to reject it. These are technically correct lines. in statistics. Okay, now if p-value is less than alpha, what do we have? We have the critical value to the left. Our critical was 1.96. The red area should be, the red one should be 0.025. The blue one is, red is half of 0.5, blue would be half of 0.47, then this is definitely going to be less than red. You also see that the diagram, you can calculate 0.047 divided by 2. If this is the case, then you know if p-value is less than alpha, you already know that the value of the test statistics that you have, it falls in the rejection region. Okay, it's the same analysis presented in two separate ways. Okay, any questions till here? Make sense? Now let's move forward. Power of the test and sample size. First I'll define what do we mean by power of the test, and then how is it related to the sample size. Okay, let me first create a sort of table. If we have a hypothesis, in reality either is going to be true or is going to be false. It's a different matter that we use technically correct language after analysis. We don't say it's true, we just say we fail to prove that it's false. Okay. If we're doing our analysis, we're going to, this is the actual case, what would be here, what we would end up doing. Either we would reject H naught or we fail to reject H naught. Okay. This I would say is a good outcome. This is true and we fail to reject it. This is how it should be. And if it's false, we should reject it. These are where we should be. But these are where we can accidentally be. And what we're doing, okay, let me just draw this. Critical value, critical value. The red one is the rejection region. Here also it's rejection region. Critical value, critical value. Okay, now if H naught is true and we get the value calculated from the sample, this is where it's entered in this. Okay, we just say we fail to reject it, which is fine, and the area, this area, what is it? It's 1 minus alpha, because level of significance is alpha, and we said that that should be area under the curve to the extreme side, to the right of critical value, to the left. So remaining becomes 1 minus alpha. So the probability of failing to reject H naught when it's actually true is, we get our value here, that is 1 minus alpha. Okay, if it's true, either we reject it or we fail to reject it. This is going to be alpha. Alright, now if it's true and we are rejecting it, we are making an error. Statistics, this is type 1 error. Alright, if, and I'll explain after this slide how we actually get beta. Okay, but now I'll just say, if H naught is false and we still fail to reject it, that probability would be beta. Okay, and if H naught is false and we reject it, there's only two things we can do if it's false. If this is beta, this has to be 1 minus beta. Where's the error here? The error now is this. It's false, but we're not able to reject it. This is type 2 error. Okay, now I'll